Here we have question 2, which says the components shown below are to be connected in a circuit to investigate how the current, so looking at current, in a tungsten filament lamp varies with the potential difference V across it. So these are different components. Now these components are actually given in our data booklet further towards the front. But anyway, we've got to put these in such a way as to measure the current and the potential difference. And then it says construct a circuit diagram to show how these components should be connected together in order to obtain as large a range as possible for values of potential difference across the lamp. So let's draw up a circuit here. So we're going to obviously have our cell. Now this over here is a potentiometer. Now what it does is it varies the current, and this arrow coming in here is showing how much, as the current comes in there, if your current is going, for instance, in this direction around the circuit, then as it comes in there, it's got to go through this section of the resistor still to get out. So you're actually varying the resistance by where your potentiometer, if you're coming in there, obviously it's got to go through a greater resistance, and therefore you're varying the current that is going through this section of the circuit. So let's take that away. Alright, so here we are. So we're going to have our potentiometer in place here, something like this, and then we're going to have our filament lamp there. Now this is going to come in, and it's going to come in somewhere along there. Now that's the basic circuit. Now we actually have to measure the potential difference in the current. So, and it's got to be through, must be through the filament lamp. So I need a voltmeter across the filament lamp, so to measure any potential difference across there. And I'm going to need an ammeter in the circuit to measure the current, because the current flowing through the ammeter will also be the same current that's flowing into the filament lamp. And in that way I will measure both those values. Alright, going down to the next page here. It says, on the axes, sketch the graph of I against V for the filament lamp in the range from V0 to its normal working voltage. Now this is not an ohmic conductor. A filament lamp is not an ohmic conductor because the temperature is changing. And because the temperature is changing, as the temperature increases, as you increase the current through the filament lamp, the temperature increases, and therefore the resistance increases. So if I drew this as V against I, I'll get something like that. You can see here that as my voltage is increasing, my current is not increasing in a proportional way. The resistance actually is increasing. So because I is equal to V over R, as my resistance increases, as my resistance goes up, my current, not a matter of going down, but it doesn't increase to the same value. So here I've got the reverse of this. I've got I over here on my vertical, and I've got my V on my horizontal. So we'll have this shaped graph like that, something like that. It's a as I said, non-ohmic device, and an ohmic device where your V is proportional to I is something like that, and that occurs for a constant temperature. Now it says the lamp is marked with symbols 1.5 volts and 300 MW. This M, remember, is milli. This is times 10 to the negative 3. Calculate the current in the filament when it is working normally. So here we are going to be using these formulas over here. We've got our power is equal to V of V times I. V times I. So obviously I'm working out my current. So I is equal to the power divided by your V, your voltage. So I'm going to get 300 millivolts, so which is 0.3, sorry, milliwatts, 0.3 watts, divided by 1.25. I'll do that on my calculator. and we get 0.3 divided by 1.25, and I get 0.24 amps. It then says the resistivity of the tungsten at the lamp's working temperature is 4 times 10 to the negative 7 ohm meters. The total length of the tungsten filament is 0.8 meters. Estimate the radius of the filament. Now, let me just clear this all. Remember, we got here I is equal to 0.24 amps. That's going to be important. So here we have got our resistivity is that, and we've got our length is that. So which formula am I going to use? I'm wanting to find the radius. So obviously this is the formula that we have. This is our resistivity over there. We've got our length there. We're going to need to work out our R, and from our area, because the cross-sectional area is usually a circle, so this area is equal to pi r squared. So therefore I can say that R is equal to my resistivity times my length divided by pi r squared, and therefore R squared is equal to rho L over pi times R, and we can take the square root of that to work out our R. Now we actually have this and this and this, but I don't have my resistance. But I can work out my resistance from these values, because we're talking about at the working temperature. So we're talking about when, at this case over here, when we have this situation here, when it's working at its correct power. So I can find my resistance here. R is equal to V over I, and I can put in my 1.25 volts divided by 0.24 amp, and calculate that. 1.25 divided by, and I get 5.208 ohms. Now that value is actually going to have to go into here. Let me come over here. So I get R is equal to rho, and that was 4 times 10 to the negative 7 times by 0.8. It's always good just to check your units here. See, it's in meters and in meters, so that's fine. Divided by pi times my 5.208. Notice I'm using a greater degree of accuracy in the calculation. At the end, I may round it down to make it less accurate. So I'm going to put that in. So we're going to get, just when you're putting this into your calculator, just remember to use brackets. Basically, you're going to need to put brackets around there and there. So we're going to find the square root. I'm going to open up a pair of brackets there. So it's 4 exponent minus 7 times 0.8. Then I'm going to close brackets and then divide and open brackets. I'm going to go shift pi times 5.208. Close brackets and close brackets. And I get a value of 1.398 times 10 to the negative 4, and that's meters. Now we've got here, this is 1.5, so I've got two significant figures. Here I've got three significant figures. I'll work to the two significant figures, so that's going to be 1.4 times 10 to the negative 4 meters will be my will be the radius. R is equal to 1.4 times 10 to the negative 4 meters. Then finally here we've got the cell is connected to two identical lamps and connected in parallel. The lamps are rated at 1.25 volts, 300 milliwatts. The cell has an EMF of 1.5 volts and an internal resistance of 1.2 ohms. Determine whether the lamps will light normally. Okay, so let me get some space to work here. There we are. Perhaps I can draw the diagram over here. So we've got something like this. We've got our cell, and let me put something in here within my cell. We're going to have our two lamps. They are connected in parallel like this. In the cell here, you've got a resistance of 1.2 ohms. So it's 1.2 ohms. The overall EMF of this is 1.5 volts, like that. Now, we know what the resistance for each of these lamps at normal working temperature was about 5.2 ohms. I've rounded that down a little bit, 5.2 ohms. We will need to work out what the current is in our circuit. But before we can do that, we're going to actually need to work out our combined resistance. Now, whenever you've got two resistors in parallel and they are the same resistance, basically it works out that you're just going to halve the resistance. I can put it into the formula. Let's just do that, but you'll see that 1 over 5.2 plus 1 over 5.2, because they are in parallel, we're going to get 2 over 5.2, 1 over RT, or the parallel. So RT is equal to 5.2 over 2. You see how it just divides? So it's going to equal 2.6 ohms. So you're actually getting a resultant resistance there of 2.6 ohms in the circuit. Now, from this formula over here, this is my EMF formula, this is the EMF, this is the current, this is the resistance in the circuit, and this is my internal resistance. From that I can work out the current. So I've got 1.5 volts is equal to my I, and I'm going to have 2.6 plus 1.2. That's for my internal resistance, and I calculate that. So I've got 1.5 divided by 3.8. So I get my current is equal to 0.39 amp. Now remember, with that current, it's going to actually split up. Some of it is going to go through there, and some of it is going to go on there. So let's just call this 0.4, just to round that. So actually I'm going to get 0.2 amps there, and I'm going to get 0.2 amps there. So through this filament lamp, we're going to get 0.2 amps. We're going to have a voltage across. It's in different ways I can do it. Let's actually just work with this. I've got my I squared R. I can work with that. I'm going to get my power is equal to I squared R. So it's going to be 0.2 squared times the 5.2, and that will give me my power that I'll actually be using for this filament lamp. So we get 0.2 squared times 5.2, and I get 0.208 watts. Now, for it to work effectively, we had to have 0.3 watts, and so therefore there's going to be less power, less energy, joules per second, and therefore the lamp will not light normally. Okay.